So basically the idea behind this is just to have a kind of like a data logging flight computer for rockets. And so when we collect data like that, it would just allow us to better like validate the flight of the rocket. If anything goes wrong, we have the data to analyze. I can assess stability. We can assess if the rocket flew the same kind of flight path that we developed in our simulations, and all of that kind of good stuff. So essentially that's the idea behind it, but then I also wanted to expand on it in a few different ways, kind of like future-proof it for other projects to do rocketry with as well. So one of those being like thrust vector control, which is pretty popular at the moment in like the hobby rockets community. So like it'll be where you have two servos on and the rocket motor's in a gimbal, and you can just actuate each servo to point the direction that the rocket engine is firing in, and so you can produce like body torques, and you can use that to actively stabilize the rocket as it's flying up. And so I wanted to try like make sure that the computer was good enough not just to do like all the data logging, but also to produce like, or to implement like a control system on it as well. So it's got to be relatively fast to do that and take in all the measurements and then produce control outputs. But I'm not sure how far along I'm going to implement a lot of those things here. I'll probably get to it because, I mean, at the moment, we have pretty much everything we need. I just need to put some headers on for the servos to connect to. But recently, I've been kind of on the fence about, so this microcontroller here is the STM32F0, and the way you program it is with the STM32 cube, which I think is in one of the other videos. But the software layer for that is very hard to get your head around. So it's kind of like you're programming it in C, but then there's like this hardware abstraction layer where you have to make calls to different registers and pin buses, and doing certain things with it is a bit harder than normal. But some of these chips also support like the Arduino environment, programming environment, along with a few other easier things to program in. So I'm going to stick with this for now, but I don't know, I might swap out eventually in the future. But kind of to run through everything, we've got a USB port here, which ideally I want to use for programming. This is a CAN transceiver to potentially connect things on a CAN bus, but I don't have to worry about that too much at the moment. Barometer for height, flash memory, just to store all of the data before we land. So this is a chip that actually gets soldered to the board, and in rockets there's a lot of oscillations and vibrations, and so normally you'd want to log straight to an SD card, but since this is like a mechanical connection in which like you just push the SD card into the slot, the vibrations can corrupt the SD card, and so we want to write everything to flash first and then dump it to the SD card once the rocket's landed. So we got that. Pyro channels. This is how you actuate like your parachute or different staging devices. It's basically just like a transistor here, which you can turn on, and it will pull current from the battery and heat up some nico wire. I need to redo this though, because it won't work at the moment. The idea with this circuit here, I have this RC circuit, which is meant to limit the current going through the nichrome wire, in the sense that you're going to charge this capacitor, and then when you turn on this transistor, it's going to dump all the current from the capacitor through the nichrome wire. And I followed a schematic online to do this, but I realized that I think this is for triggering E-matches or potentially setting off like black powder charges. And I won't heat up a nichrome wire because obviously the time constant of this is like 0.02 microseconds or something. Let's see.
Yeah.
for, I don't know, you can do the math. Anyway, then you're just like pulling current through this 200 ohm resistor, and I think we're going to use a 2S LiPo, so that's like nominally 7.4 volts. So basically, what I'm going to do is I'm going to do that right now. I'm going to dump that, and I'm going to do a pretty just like simple circuit where this resistor here, so at 7.4 volts, I think we want like 2 amps running through. So what's that? V equals divided by 2, like 4 ohms or so. That'll give us like just under 2 amps. And yeah, I definitely need to like scope that out a bit more, but this should limit the current. And so even if something like if this transistor fails to short, because transistors can fail in one of two ways. They can either fail open or fail closed. If they fail open, that's fine because then no current's going to be running through the transistor. But if they fail short, then this is going to be permanently closed, and you can just like drain your battery, or even worse, if you don't have a current limiting resistor here, you can short the battery and it'll explode in your face.
Yeah.
Anyway, I think this is a better approach. It's just a current limiting resistor, and this voltage divider here is basically just going to be. Did I do the math on that correctly? So what voltage? So let me just think. This doesn't make any sense because this is always going to be high because it's connected to the battery. What we actually want is the voltage divider to be after the switch, right? I think. So now we have current going through here. When this is closed, we're going to have current running through here. You know what? Let's not worry about that right now. Basically, this is meant to detect when this is shorted. But in this case, obviously, nothing's going to change unless when this gets shorted, all the voltage is going to be across here. Yeah, anyway, let's not worry about that right now. Other components on here, this is just a accelerometer plus gyroscope plus magnetometer. And it does like onboard carbon filtering. And so it basically just spits out quaternions, which is really nice to use. And 3.3 volt regulator. So this is just stepping down our either 5 volts from the USB to 3.3 volts, or the battery 7.4 volts down to 3.3 volts. And it's a linear regulator. I'm slightly concerned about heat just because, stepping down from 7.4 to 3.3 is just going to be dissipating all that current loss, voltage loss as heat. It should be fine though. I don't really want to do a switching converter, which is much more efficient. So basically that turns on, turns off really quickly. And so you're not actually dissipating any heat. You're kind of like simulating a step down voltage just because you're switching really quickly. But I don't want to do that right now. And then, so this microcontroller here would basically just have like a bunch of decoupling capacitors, which smooth out the voltage on the power supply. And then like ITC pull-ups and a crystal here. And then we have our headers. I think I'm going to add more headers. I want to add servo headers. So basically just plugs that a servo can sit in. Actually, that's another interesting point that I haven't considered is we need to have control signals for the servos. So servos normally just take like PWM signal, and that indicates which angle they should move to. But yeah, I don't think we need that right now. I think we'll focus on data logging and then we can do more fancy stuff later. So that's where we're at last week. And this week, I have a few people join now. Cool. We're going to get about routing it. And so I think last time I just had like a big mess of components like out here. And I was like, all right, the first step that you need to take is to organize all of the components basically into like their schematic parts. So here, you know, like we're going to take our microcontroller and then make sure all of the relevant parts that are going to be close to it, like decoupling capacitors and all of this, just group them all together. So that's what I've done. I've separated everything out. And so these are all our microcontroller parts. These are all our, oh yeah, that's our pyro. What is this? Oh yeah, that's our giant transistor, SD card. This is our power circuitry here, I believe. Yep. And then I don't know where these guys live, but that's all right. We'll slowly get around to routing all of that. So here we go. So this is our, if you press Alt-3, you can look at it in 3D. So these are all of our parts. Now, the task basically is routing all of these together with traces and organizing them in a way which is neat and tidy and I was thinking some of these footprints, like I want to swap out too. Like these headers kind of look ugly. I want ones that are like pointing off the board, not vertical but horizontal. So kind of like this one here. But I don't want them side by side. I want them up and down, like vertical, like horizontal but vertical. I'm pretty sure those exist. Anyway, today's going to just be like pretty chill. I'm just going to like work on this, and if you guys have questions as I'm doing it, feel free to bring them up and ask away. I've got to kind of plan how exactly I want to approach this though. Obviously the board right now is, I've made it pretty big just so I can like visualize where everything's going to sit, but I'll probably make it much smaller and make sure that all of the components are kind of like, you know, you don't really want too much like wasted space on a PCB for whatever reason. People love packing things really tight. Now, all of these lines are called rat lines, and they're basically guides telling you which pads need to be connected together. And so that's kind of, yeah, a way that you can start figuring out what needs to go where. I think what I want to do is start with the USB connector, and then we can kind of like start with that and then follow where the power is going. And that might make things much easier to plan out. Yeah, let's do that first. Let's just look at this micro USB connector. So where do I want to plug this in? Let's say I just mouse over and press M, and you can move things to where you want. How's that? Cool. So that'll be our little micro USB plug. And then behind that, we want to, and yeah, so USB, that's 5 volts, 5 volt logic, and the STM32 runs on 3.3 volts. And so if you gave it 5 volts, it would break, it would die. Ah, yes, and the other thing is the battery connector. That's what that is, okay. Yeah, I don't like these plugs for a battery connector. Like you could use like a JST plug. These are like pretty typical connectors that people use for connecting batteries. You can probably buy like from Core Electronics, just like the standard lipos. Yeah, I think they use these plugs. I don't really feel like adding the plug for that right now. I do like these headers, like these block terminals. Oh, actually, no. I think what we want to use are screw terminals. So a screw terminal, it's kind of like, yeah. So they're kind of like this. It's kind of like a block, a head block, but you put your wire in here and then you can screw it down with a screw, and that usually provides a much more solid connection. So we actually want to use those. I'm fairly certain KiCad has those as one of their parts. Yeah, I'm just gonna have a look at that. So where are we at? We want to change J5. Let's just change J5 for a start. So we've got these connector pin sockets. I want a screw terminal block. Pretty sure you can view them. Yeah. This doesn't look anything like. Is it? How do I look at it in 3D? There we go. Oh, they don't even give me it. Connector. But if you can ever find it, you just look up screw terminal and KiCad. Yeah, this is the kind of thing we want. So I wonder if they actually have them built in their library or not. If they don't, I'm not going to bother creating them yet. But it looks like they should. Try terminal block Bornea. All right, let's try that. Terminal block Bornea. No. Oh, yeah. Okay. Now, if it doesn't have a 3D footprint, that's probably fine. 2 5.08 pitch. Perfect. All right, let's chuck that on. So once you select your new footprint, remember you just want to generate a net list. Save over the old one, and then we go over to our PCB design and we want to import this, update our PCB. So that would have added our terminal block somewhere. That's not it, is it? I could have swore I just saw it get imported. Let's try again. Ah, there we go. So yeah, sometimes your the part that you're replacing, it still exists on the schematic, and so you just want to delete it and import the new one. Maybe like that. Okay, let's just chuck that there. Anyway, so this is for the battery. It's a screw terminal where we can screw things in. Cool, that looks good. So once we've got 5 volts coming out of the micro USB, let's go look at our schematic and see where this is going. So we've got our 5 volts going from the USB, and it goes to our Schottky diode. That's a word that I've never said out loud before. Schottky. Basically, Schottky diodes, they're very, very low forward voltage diodes. or probably like 0.3 volts. So that means that they allow current to pass through this way. Once you have enough voltage here, like 0.3 volts, then it will allow voltage to flow through. But for whatever if you have a higher voltage here for whatever reason, it won't let current flow the other way until you hit like 30 volts or something. And so it's very useful for protecting circuitry and allowing current only to flow one way. So and then we can see that we want to connect this 5 volts here to this here. And so I think, if you press Shift X, it'll bring up the routing tool. You just click, and it's good to align things a bit better. So let's do a 20 mil grid. It's a bit straighter. None of these components are on the grid though, which is all right. It's a bit annoying. Boom. All right, cool. So trace width is another interesting topic of discussion. So trace width is basically how big these copper wires are, copper traces. And I think, so I have this set to 0.25 millimeters, but the way that you decide this normally is for one, the amount of current that you're going to be supporting through the trace. So if you have higher current, you normally want a thicker trace to handle that, handle the current. Primarily because I think the thinner the trace, the more inductance it has or something like that. And so if you're trying to push a lot of current through a very small trace, it's going to heat up a lot. So the wider the trace, the better the thermal properties as well. So it'll be able to dissipate more heat. But the way that you normally decide on your minimum trace width and other parameters like that is you design for the manufacturer that you're going to go with. So JLC PCB, in their resources, they will have probably support actually. Capability is right here. So yeah, every board house will have a tab like this, and it will give you your specifications that you have to work with. So for example, here, since we're going to be designing for JLC PCB, they have a tab here, minimum trace width and spacing. And so their minimum trace width for the inner layer, outer layer, outer layer. So we're just going to have a 1-outs board, and we are going to have inner layers, but one, 2 layer. Yep. I think these have actually gotten better from last time I checked. I thought they only had a 6 mil limit. But okay, so you can see here, let's just roll with that. 5 mil trace width is the lowest that they can go, the smallest that they can go. And so I think what we have here, we have our trace width set to 9.84 mil, 0.25 millimeters. So that's going to be totally fine. They'll be able to manufacture this, no problem. Yep. Yeah. You can use different trace width. I guess like try to stick with one, but for your main current traces, for example, this one, I'll probably want to beef this up a bit more than the traces I'm using to connect all of these components. But you can basically, like, how they make a PCB is they just have they pour copper everywhere, and then they use like lasers to kind of chip away at the copper and leave the traces that you end up with are actually the copper that's left over. And so yeah, basically in that process where they're like chipping away the copper, it doesn't really matter what size you have in different spots. I'm looking at the schematic. So, oops. we're going through our Schottky diode and then our fuse, which was F1. Yep. And we can just route these. And then our ferrite bead. So this helps. This is a component that just helps to minimize noise as well. It's kind of like a little inductor. Gets rid of high frequency noise. Oops, Shift X. And then we're going into our capacitor, our input capacitor, and then we have our step down regulator. So let's put those up here. And we'll have a quick think about how we want to route the power on this board. What was it? C7 and C14. Okay, cool. Cool. So, oh yeah, C7. We're going to have the output of the ferrite bead feed directly into, yeah, it's basically this line here. It goes into our step down regulator and our input capacitor. Now, with decoupling capacitors, you want to put them as close to the input pin of the chip that you're decoupling as possible. So there's actually a tiny chip. Yeah, pretty tiny. That's all right. So we can see that this actually wants to go into pin 1 of the step down regulator. So what we can do in that case is rotate this and connect our capacitor directly here. Right, so it's nice and close, and that minimizes the noise. The closer it is, the better. Cool, and we're about to hit a interesting point on ground planes, but obviously because like this chip needs to connect to ground, this capacitor needs to connect to ground here. Micro USB has to connect to ground. Oh yeah, and these are going to connect to here. Cool. Okay. Sweet. So let's ignore the enable pin for now, and then we go through the regulator, and on the output we have C14. So this just smooths out the 3.3 volts coming out of this. And so where was that? That guy's here. And what that was pin 5. So yeah, nice and close. Cool. And now I have this other resistor here. Basically, this is making sure that our enable pin, this basically turns on and off the regulator. Just make sure that's always on. And so where did I put that? R5. And this wants to connect to here. And then this pad, we want to connect that to V in. Maybe we can route it like that. Or like that. Yep, that would be good. Cool, and so now we should have a pretty clean 3.2 volts coming out of here, which we can use to power everything. But before we get onto that, I want to establish a solid ground plane. probably on the first inner layer. So actually, I'm not sure if I mentioned last week, but for PCBs, you can generally either go with a 2-layer board or a 4-layer board. A 2-layer board, you can just put your traces on the top and the bottom. But a 4-layer board, you have 2 inner layers, which you can use to put more traces on. A lot of people think that 4-layer boards are like quite advanced. They're not. And most 4-layer boards like JLC, PCB, it's probably not that much more money to do a 2-layer board versus a 4-layer board, because most people just do 4-layer boards these days. I might be a bit more. Green solder mask, white screen, 280. Yeah, okay. Well, it's like $5 more, but the like utility that you get for routing 4 layers. Oh, okay. And by utility, I just mean the ease of routing. It makes it so much easier to have those extra layers to put traces on. Just because, like, you can imagine if I have traces going all through here, I might just get stuck where I'm like, all right, I have no idea how I can get this trace to go all the way out here. But it's all right to do that with a 4-layer board. But with a 4-layer board, one of the main things that you want to do is have a massive ground port. And if you have a big ground layer, that really helps with like signal integrity and preventing things called ground loops. And normally you just put that on the bottom layer of a 2-layer board. But then, you know, if you need to route some things on the opposite side of a 2-layer board, then you're going to be breaking the ground pour. And normally you want just like a completely nice uninterrupted ground pour. So I'm going to click add filled zone. I'm on the first inner layer. I'm just going to like make my grid easier. Something I need to learn to do. Oh yeah, and I'm just going to click first inner layer, ground, and then click around the outside. Yeah, something I need to learn to do is better set up my grid sizes. Boom. All right. So now we have a ground pour. So all of this copper, you probably can't see it because, yeah, you can't see it in the 3D view because it's like wedged in there, one of those layers. But the great thing about this, oh yeah, you can see like ground, it's already connected to these through hole parts here. Now, say for example, I now want, this ground here on the, they're doing 10 mil, on the micro USB. I need to connect this to ground somewhere. And instead of connecting them all with like a trace that goes from here to here to here, and then all the way around to here, I can just simply start routing, press V, and now I'm on the inner layer, and I'll just click to put a, boom, click to put a VR here. So now this is like a little tunnel that goes all the way through the board, and it connects to every layer. Or it provides like an access point for each layer to connect to. So now I think if I rebuild my ground pour, which there's a shortcut for it, might be, did I just do it? Yeah, if you press B, it'll redraw the ground pour. And this will now be connected, so you can see that on the first layer. This ground is now connected. So then let's do that for all the other grounds. Press V. And yeah, that's connected to ground. Do it again for here. Or, you know, you could just like connect the wires like that. But I think a good practice is to have a different via for every capacitor. I think, well, this is a resistor here, but it's probably a good idea to have a individual ground for every single component or every single capacitor, or, you know, this kind of thing. And another thing actually I need to learn is via sizes. So I didn't really set up the size of this via, but you know, they're kind of just like little tunnels, but they can be of varying size, and it depends on a couple different things, I guess, just like your how much current is going to be going through it, and I guess a few other factors like that. I'm kind of just going with default ones now so I can get somewhere and not get bogged down with too much of the boring stuff. Hit V. And we have our ground here. Now, see, this is kind of where routing gets tricky, because I don't really want to, like, you know, the V is not really going to fit here, and I don't really want to put the V beneath the chip either. I can give you a reason for why that doesn't seem like a good idea. It might be totally fine. I haven't done it in my experience, but I'd feel more comfortable with routing a trace under the chip rather than putting a via under the chip. That might be totally fine, actually. I'm just not very experienced with that side of things. Cool. And now I can just route this here and put a via and be pretty comfortable with that. Boom, boom, boom. And what else? Ah, yes. So we have this. Actually, and then another thing you can do is you can click show the outline. So now we don't have these. Oh, I have no idea what these lines are. Weird. I don't know why they added this. These weird traces that. What is that? Ah, show outlines of filled areas only in zones. Anyway. Yeah, that's interesting. I'm not sure what these lines are. Like, they look like traces on the inner layer. I can't highlight them or anything. And it goes to all of the pads. That might just be something that happens on 4-layer boards. Anyway, I'm just going to click that so I don't have yellow blaring in my face. And so this transistor here, it basically just acts as a switch between battery power and USB power. VBAT. Cool. So what we're going to want to do is on the top layer, route VBAT. Like that. And then just drop a V out for ground here. And then this trace goes up to our 5-volt line here. And then this just happily connects there. What else is connecting here? VBAT. Oh, okay. Cool. This connector here is for the pyro channels. So obviously the pyros are going to be pulling straight from the battery. Let's chuck that there. I'll chuck all these components on this side. So this is kind of what happens as you start routing everything. You realize that there's better spots for all of your components. Because we can just pull our battery voltage or our battery current right here and then burn an ichrome wire, an E-match or something. And then when this is mounted in the rocket, that can be where we actuate things. So this is mostly done. Net. I'm not really sure if this is necessary, but it looks like they want all of these pads to be connected. Probably doesn't matter, but it's fine to do. Net J7 pad 6. Yeah, that's fine. Cool. And now we have most of our power circuitry organized here, apart from, oh God, our silk screen. So these white numbers here, that's on what's called the silk screen layer. And the silk screen layer is where you can just put informative, just like text and graphics and things like that. So it's purely aesthetic. And I would like to move. So obviously R5 is for that resistor. So we see like a blue line, which is showing that they're connected. You can put silk screen over vias and things like that. It's totally fine. You can see here. You can put it over traces. Yeah, the text will show up on the board. So it'll be all of these like little white things here. And you can even import like a DXF, like a drawing. So if you want to put like a logo or like your name, normally what you can do, so you can just click text here and make sure that you're on the silk screen layer, front silk screen, and say this is just like our flight computer version 0.1. Version 0, yeah, 0 version 1, cool. And we can just check that like here. Cool, and then when it prints, it'll just have that there. I should name the flight computer something. No idea what to name it. Yeah, maybe we'll take a vote. Let me fix these up a bit more. So this is for C7. Don't know how I made it over there. R2, R3, C14, D1, J7, Q1, that's cool. FB1, F1. For example, here, we'll probably change this to Pyro. Right, and then that will just indicate that this is where our Pyro output is. Wait, no, sorry. This is our battery. And then this is our Pyro. I'm just pressing E to edit text. Cool. Battery and our Pyro and all of our electronics here, our power systems, sorry. Cool. So now we have most of our power systems organized, at least for the 5-volt USB, and maybe also our battery. But the only other thing I haven't routed is these USB differential lines. I haven't done that before. I'm going to leave that for now. USB is a pretty high frequency protocol, and when you run differential lines, you have to worry about a few extra factors. I'm assuming it'll be fine. I can just run these on a different layer beneath all of this and get to these pads, but yeah, I wouldn't worry about routing that just yet. What I am going to look at though is this 3.3 volt output here. This is, this is our 3.3 volts. And so basically what we want is that 3.3 volts to connect to all of the VDDs on, so VDD is just your input voltage, on our microcontroller. So here they are. We want to connect all of these to VDD, and we want to connect them all to VDD through their decoupling capacitors. So let's just find out where they are first. So we've got pin 19, 32, 48, and 64. So there's 1, 64. 19, so there's one all the way on that side. Hmm. 32 and 48. One there and one there. So it seems like they're all around the outside, which is kind of annoying, but completely doable. So we've got that coming in there, and then basically all of these decoupling capacitors, I want to make sure that they're close to the pin that they're decoupling, like this. These ones are for here, I'm assuming. Let's see, 15 for. So C15 is connecting to pin 30, which is our, our reference. And we can kind of just like slowly hook things up. So I know that these capacitors are going to want to be connected together and then be routed to that pin on the microcontroller. I know that these want to be connected together and go to this pin. I know that these two are going to want to go together. Wait, C3 and C5. C3 and C5. What's C19 and C18? C18, C19. Oh yeah, and they'll probably get a VBAT as well. VBAT is number 1. So we got 1 and 64. Okay, cool. So let's move these over. C6. All right, so we've got 1, 2 capacitors here, which are going to want to connect to pin 1. Let's do that. Dun, 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 dun. And then we've got this one and this one. I need to double check the arrangement of these actually as well. I think normally you want the smaller capacitor closer to the pin. Yeah, I think. But it's really easy to swap these over, so I'm just going to have it like this for now. And I don't like how, look at this bend here. It's not really an issue, it's more of like a preference thing, but I think that sucks. So we can hit G. No. Let's delete this trace. And I want this to come out straight, please. Cool. All right. And then for the sake of connecting things, we have our output of the 3.3 volt regulator, and it's going to go into here. And so now we finally routed our power into our microcontroller, at least at one corner. But think about how best to provide power to each corner. Something that you can do, which I might actually end up doing, is, so you know how we did a ground pour on the first inner layer, you can do a ground pour on the top layer for power. So we can just have like a big ground layer on, a 3.3 volt pour on the top layer, and then everything can connect to that easily. Another alternative is to have a big ground pour on another inner layer, so maybe inner layer 2, that can all be 3.3 volts. And then if we want to connect, this pin here to power, we just drop a VR and it will just connect just like that. And in fact, that sounds like such a good idea to me right now that before I finish today, I'm going to do exactly that. Yes. All right, so plan is basically all of the things here are run off 3.3 volts. So why don't we, inner layer 2, let's drop a polygon. And essentially, this is where our 3.3 volts is coming out. Why don't we just have a pour that's kind of like, we want this to be 3.3 volts. And oops, I'm going to change my grid size to make it a bit nicer to do. And we're going to basically encompass this whole thing. Yeah. This may or may not be the best idea, but it's part of PCB design. It's just experimenting with different things and seeing what will work for you. And then I'm going to connect this with a strip here. Interesting. All right. Now, if I want to connect all these to 3.3 volts, all I have to do is drop a VR. And now connect these together. I want 3.3 volts to come here, so I can just go here and then drop a VR. Go here, drop a VR. Go here, drop a VR. Neglected these ones. And track. Ooh. These are going to pin 19. Drop it there. And the last one here. Cool. And then all of these have to connect to ground as well. Yeah, you can just do the exact same thing. Oops. And then you can just do that for all of the capacitors. And then our power situation is pretty much sorted. I'm kind of concerned if they're going to treat this as two separate blocks, and there might be a discontinuity here. I'll probably want to combine that somehow, but yeah, that's all right. So now, yeah, all of our power can just be connected like this, which saves us having to run like weird traces everywhere, and makes it much nicer to break things out in terms of wiring. For example, if we had, a wire that came in here and then connected to this pin here, that whole pathway would all of a sudden be blocked off. And if we wanted to route our I2C lines, they'd get stuck here. We'd have to drop them and then go under and then come out. But I think this gives us a bit more freedom sometimes. Ew. Have you seen board with the ground planes on top and bottom layers? Yeah, normally what they do is basically fill up, once you're done with your board, they kind of fill up all of the remaining space with the ground. It's because the more ground that you put down, the better, really. With like asterisks, there's important things that you have to consider. If you have too many ground layers, you want to make sure that you stitch them together with V's. It's called ground stitching or plane stitching or something. There's a few different things that you still have to consider, but most people, they'll put ground pause on the bottom layer, they'll put it on the top layer. It's pretty standard. So for one, this looks disgusting. We would want to move these capacitors up a bit just so we don't have this weird angle. It's better to keep things at like 45-degree angles and just keep it all standard. This just looks weird. But essentially, yeah, that covers the whole power situation. Then we can just break lines out and connect them to wherever we want to connect them to. But yeah, I think I'll leave it there for this week. We got through routing the power section at least, and we started to power the whole microcontroller. So I think this is a pretty good solution moving forward. Obviously, like you can tell that routing is not an easy thing. It takes a long time and it takes a lot of patience and rearranging. Like I could work on this for another like 3 hours, hit a roadblock and be like, nah, I have to start again. Just remove all traces and then just, go from scratch. It's pretty standard. It's, like PCB routing is not easy, but the more you do it, the better you get at it. And yeah, like obviously, even I am still practicing and trying to get better at this. But yeah, it was good progress today, I think. So thanks everyone for coming along. If you have any other questions, feel free to shoot them at me, and I'll try to help you out as best I can. Hopefully you learned something. Yeah, thanks for coming along.